still grading your midterm exam. So we will have your grade ready by next Monday. So I'm not going to drop your grade this weekend, but I'll drop it next Monday. So we'll discuss the distribution and policy for regrade and everything next Monday. So stay tuned. All right. Other than that, do we have any questions before we get into materials today? Nope? We're happy? Okay, sounds good. So we are done talking about chapters 1 to 3, right? So chapters 1 to 3 are basic introductions to thermodynamics. Just refresh your memory, we went over definitions of different terms of like what is system, what is the surrounding, what's adiabatic, what is isobaric. These are like basic vocabularies of thermodynamics. And then we spend a good amount of time talking about laws of thermodynamics. So in total, we have 3 laws. Well, counting the zeros, we have 4 laws of thermodynamics. So far, we went over 3 of them. And we'll leave the third one, leave the third law of thermodynamics to later sections. But by talking about the laws of thermodynamics, we went over and defined several state functions, thermodynamic state functions, including internal energy, enthalpy, entropy, temperature, etc. Also discuss equation of state. And today we're ready to move on to chapter 4, where we're actually talking about equilibrium, or more specifically, this chapter focuses on material equilibrium. So now we're actually having some changes and trying to find ways to describe what is happening when we talk about material equilibrium, right? So in today, we'll go over 3 topics. One, we'll go over definition of material equilibrium, like what exactly is material equilibrium. And 2, we'll talk about entropy and equilibrium. This will feel a little bit like a refreshment of your memory, but taking one step further when we're talking about entropy, we know that, well, delta U of the entire universe equals to 0 when everything is at equilibrium, right? So now let's just think about what if we have reactions going on, we have material exchange going on, what is happening? And then we'll define 2 new state functions called Gibbs free energy and Helmholtz energy, or work function. So for this part, we'll follow our normal trend, right? Step 1, define the terms. Step 2, know how to calculate the change of these state functions. Step 3, what exactly are they? What's the physical meaning behind the Gibbs free energy and the Helmholtz work function? So let's get started. First topic, material equilibrium. So this part will be a little bit like a review on your chapter 1. So remember, when we talk about thermodynamic equilibrium, we're saying there are 3 different kinds of equilibrium. All 3 of them need to be checked to get thermodynamic equilibrium. So the first one, mechanical equilibrium, stating the system undergoes no acceleration. Right, so basically, if we're talking about a system at mechanical equilibrium, you can assume that, well, you have only reversible process taking place on the mechanical end. Or the other way to put it, when we're talking about only PV work and at mechanical equilibrium, that's equivalent to say only reversible PV work can take place. Right, so your system will expand at a very slow rate, no like acceleration going on when that expansion is taking place. So that's mechanical equilibrium. Next up, thermal equilibrium. So the original definition is saying adding a non-adiabatic wall will cause no change, right? So a non-adiabatic wall allows heat transfer. So if 2 systems are at thermal equilibrium with each other, now you add a wall that allows heat transfer to take place, it shouldn't make any changes to the system. And then to our focus, which is material equilibrium. So when we say material equilibrium, this actually contains 2 different parts. One is called reaction equilibrium. So that means whether or not we have a net chemical reaction taking place. 2, there's no transfer of matter, right? So you can have transfer of matter, like you can have like 2 different solutions of different concentration, and you mix them together, and then they eventually becomes a homogeneous mixture. So no transfer of matter in that process. And focusing on the first one, which is the net chemical reaction, and then you can break it down into two things. One, you can have a reaction going on, or you can have a phase transfer going on. So whether or not it's a chemical reaction or a phase transfer, they're part of the material equilibrium. I didn't expect that. Sorry about that. Okay, so for reaction equilibrium, like what the sentence reads is equilibrium with respect to conversion of one set of chemical species to another set. Or in plain English, like if you think about a burning of H2 gases in oxygen gas, you're forming water, right? So you're converting one set of chemical species to another set. So that's chemical equilibrium. As chemists, we are more familiar with this type, right? Phase equilibrium. And this part is saying we have equilibrium with respect to transfer of matter between phases of the system without conversion one species to another. Or, still use water as an example. You can have water ice melt to form liquid water. So that process involves like Q fusion. If it is a constant pressure process, now that Q fusion will equals to delta H fusion. And if I have the reverse reaction, you can have the Q freezing. And likewise, your liquid water can undergo vaporization or condensation to liquid vapor. And for this process, well, if the phase transfer takes place at constant P, then your QP equals to delta H. Right, so this part should be a quick review on what you already know. And now let's think about linking equilibrium or material equilibrium with entropy. So in our last lecture, we did all the derivation and end up to say, by using the second law of thermodynamics, we can find out that the thermodynamic equilibrium in an isolated system is reached when the system's entropy is maximized. So this is the curve that we end up getting, right? So if you plot entropy with respect to time, right? So we have the entropy increase until we reach equilibrium. So at equilibrium, we have all reversible processes, so ds equals to 0 at equilibrium. And prior to equilibrium, you have ds larger than 0 prior to equilibrium. Or the other way to put it is, if we're taking the universe as considered, we have S universe maximized at equilibrium. All right, so that's a review. Now let's take one step further, considering a setup like this. Now imagine we now have a big tank, say like a huge tank, that's surrounded by rigid, adiabatic, impermeable wall. So whatever inside the wall is isolated from the entire universe. Now in here, we then manually define a system and a surrounding. So that system can be some kind of reaction container where the surrounding is like a water tank, right? So that's just the water in there. And in here, we can manually set, okay, first of all, the system and surrounding together are isolated from the rest of the universe. 2, we make it so that the system is at thermal and mechanical equilibrium. But you can have reactions taking place at the system or inside the system. So reaction equilibrium, not sure. So I put a question mark here, right? So we can have irreversible chemical reaction or phase changes taking place inside the system. And the surrounding, or this water bath, that's kept at thermal and mechanical equilibrium. and also material equilibrium, right? So if you have a water tank and inside that water tank you have a reaction container, the reaction only takes place inside the reaction container. So for the surrounding, it's always at thermodynamic equilibrium, where the system is not. And the system and the surrounding are separated by an impermeable wall. It's non-adiabatic, so it allows heat to transfer in between your system and surrounding, but no material transfer. So that's a setup. Now we will do a quick derivation together, thinking about in this kind of system, what is going to happen when we're looking at the relationship between delta S of the system and surrounding adding together? What do we know about the entropy of the system when there is like reaction going on, when there's irreversible reaction going on? So I'm going to do that on the board, but again, it's in our annotated notes so you can see it. So first of all, we'll read the condition and use the knowledge we went over before to translate these conditions into writing, right? So the first one, we say that the system and the surrounding is isolated from the universe. So what does that mean? Now, in this case, thinking about only heat transfer taking place between your system and surrounding, and that separating wall, the impermeable separating wall is also rigid, it's not moving. So we have one thing, that's the change or the heat flow in or out of my system plus the Q of the surrounding must add up to be 0. Right, so that's just energy conservation. It's isolated from the rest of the world. We can't create or destroy energy from out of nowhere. And, or the other way to put it, we can write dq system equals to negative dq surrounding. So that's just reading our first setup of the situation. Secondly, using our second law of thermodynamics, we know that the total delta S of the entire universe is larger than 0 whenever you have an irreversible reaction taking place or irreversible process taking place. So in this case, we have irreversible reaction taking place at the system. So what do we have? We have delta S of the universe is larger than 0. Or the other way to put it is my system is not at thermodynamic equilibrium, or the total entropy of my system plus, or the differential of my system plus my surrounding must be larger than 0. So again, this is what we did before, right? So prior to equilibrium, your ds is always larger than 0 prior to equilibrium. So that's where it comes from. Again, a review. All right. Second, so that's check. Thirdly, we say that for the surrounding itself is at thermal, mechanical, and chemical or material equilibrium. So the surrounding itself is at full thermodynamic equilibrium. So we can rewrite my ds surrounding equals to dq reversible over T, because for the surrounding, the Q surrounding itself is reversible. The Q system may not be. Or we can rewrite it as dq surrounding over T. So ds surrounding equals to dq surrounding over T, because if we're considering the surrounding, all processes are reversible. And then, thinking about the system. What about the system? Now we know that for the system, we have irreversible processes taking place. So your ds system no longer equals to dq system over T. Or the other way to put it is we have ds system must have larger than dq system over T for the irreversible process. all right? Or this is what we get. So we know that this is larger than 0, and this part will be also larger than, so my D system, let's see, so my DS surrounding, my surrounding itself, that's already at 0, and we know this sum is larger than 0, so my DS system must be larger than the DQ system over temperature.
Could you say that one more time?
Okay, let me try this one more time. So let me erase this one a little bit. Let's see. So we have the S surrounding equals to the Q surrounding over temperature. And we know that for the system, my ds of the system plus the dq of the ds of the surrounding is larger than 0. But we know my ds surrounding is at 0 because the surrounding itself is at equilibrium. So if you take in consideration of both of them, that's a positive number. And now my surrounding, that's ds equals to 0. So the ds system must be larger than 0. And in the other one, we know that in here, we have dq surrounding equals to negative dq system. So if this whole thing equals to 0, right, so my dq surrounding over temperature must equals to dq surrounding over temperature equals to 0. All right, so in this case, we end up getting the S system is larger than my dq system over temperature. All right, so far. It's like, looks pretty straightforward. It almost looks like a common sense. Or the other way to put it is we can end up saying, all right, so for the system, what we end up getting is your ds is larger than dq system over temperature. And after the equilibrium is reached, and then that takes the same as again. Right, so this is prior to equilibrium. Our ds is larger than dq system over temperature. And then after the equilibrium is reached, we then have ds system equals to dq system over temperature. Or the other way to put it, if we take both of them into consideration, then we can generalize this conclusion to say that, okay, so my ds is always larger than or equal to dq over t whenever you have a closed system that's at thermal and mechanical equilibrium, and there can be material or phase change. Right. So it's larger than this value when the process is irreversible. It's equal when they are reversible. Yes?
And you're saying that's true even if the system has a material or phase change?
So this is true when we have a material and phase change. It is positive, or the ds is larger than dq over t, when that reaction is irreversible. It's equal to dq over t when it is reversible. Well, that's the definition of entropy anyway. So let's take this one more step further with our first law of thermodynamics, because in here we're talking about a closed system at thermal and mechanical equilibrium, at rest, no external field as normal, right? So we can use our first law of thermodynamics. If we're using that, what do we have? We have du equals to dq plus dw, so that's our first law. And from here, if we're moving the temperature to the left-hand side, I know it's not an equation, but the temperature is always positive, so moving that temperature to the left is pretty safe. We can end up getting my TdS is always larger than dq when we're talking about the material equilibrium or reactions or phase transfer taking place. Or the other way to put it, if I plug in this relationship into our first law of thermodynamics, then my first law of thermodynamics becomes du is going to be smaller than or equal to TdS plus dW. Again, closed system, thermal and mechanical equilibrium, material or phase change taking place, or reaction or phase change taking place. I'm going to leave that on the board because we will be using that to derive other things. All right, so this is using my first and second law of thermodynamics. We end up getting du smaller than or equal to TdS plus dW for this closed system at mechanical and thermal equilibrium and not at material equilibrium. I'm just going to say reaction taking place, but in reality, that includes all other kind of material equilibrium as well. All right. And now from there, we can move on to define our two new state functions. That's very useful to describe material equilibrium. Okay, I'm going to pause here and see if we have any questions. We're happy? All right, so far it should be more feel like a review. You'll be like, okay, I think I know these. But now let's take one more step of thinking about, like, we as chemists, we want to know what is at equilibrium. Like, how do we know if the system is approaching equilibrium? And how do I know, like, if my system is not at equilibrium, where will it go, right? Where will that equilibrium shift? So that's why we're defining the Gibbs and Helmholtz energy, whose value is directly related to material at equilibrium at different conditions. So in this case, the Gibbs free energy is talking about material equilibrium at constant temperature and pressure, right? So it's a typical chemical reaction at 1 atm in a water bath. So you can use Gibbs free energy to describe the equilibrium of that chemical reaction. Or you can have Helmholtz energy. So that's the material equilibrium at temperature and volume. So the Helmholtz work energy is more applicable to chemical engineers, where you have the certain volume and certain temperature, and you're talking about, well, what does material equilibrium mean in that condition? So again, for this part, we'll first introduce the definition of these state functions, talking about how to calculate them and what are the physical meaning of these state functions. So let's do it. This part will be basically derivation of how the Helmholtz free energy is being defined. So we'll always start from this equation here. So I'm just going to leave it there for your reference. And also some of the things we will be using, including calculus. So that's dxy equals to x dy plus y dx. We'll also be using our reversible PV work. So we have work reversible equals to negative PdV. So we can use reversible PV work because in this case, we're only talking about material equilibrium. Right? Remember, we're at mechanical equilibrium. So for PV work, which is like an expansion of the system or contraction of the system, that's always reversible. So we can use our W reversible equals to negative PdV. Okay, and let's look at the definition of the Helmholtz free energy first, which is constant temperature and volume. So we start from here. And using our basic calculus, what we can get, well, we have dxy equals to x dy plus y dx. And in the du smaller than TdS plus dW, we can write my dTs equals to TdS plus SDT. Or this TdS, we can rewrite it as dTs minus SDT. All right, and we have our work reversible equals to negative PdV. So taking these reactions together, we can rewrite my du smaller than TdS plus dW. So again, this is dTs minus SDT. My dW is negative PdV. So plugging these numbers, we get du smaller than dTs minus SDT minus PdV. So far, so good. And then I can move this one to the left-hand side, or subtracting dTs on both ends of the formula to get du minus Ts smaller than or equal to negative SDT minus PdV. So far, so good. And now thinking about the Helmholtz free energy, we're talking about this one of the functions that describes material equilibrium at constant temperature and volume. So at constant temperature and volume, the right-hand side, my dt and dv thus become 0, right? So for this case, on the left-hand side, we got what we want, which is a function defined by u minus ts. This is going to always be less than or equal to 0 for any constant TV processes in a closed system, thermal and mechanical equilibrium, PV work only, but reactions taking place. All right. Or the other way to put it is the justification of material equilibrium at constant T and V is this one, the du minus Ts equals to 0 at material equilibrium. Constant TV. All right. And like closed system, mechanical thermal equilibrium. Or the other way to put it, this is what we want, right? We want a state function that describes the material equilibrium, and thus we defined our Helmholtz free energy, which is A equals to U minus Ts. All right, and I'm going to add that definition to our board here. We have A equals to U minus Ts. So A equals to U minus Ts, that's always true. And your delta A, or your differential of A will be smaller than 0, and it's going to be equal to 0 at material equilibrium. Or the other way to put it is we can write the same kind of figure, right? You can have A with respect to time, right? So at material equilibrium, for constant TV processes, at material equilibrium, we know my A is dA equals to 0. And I know my dA is smaller than 0 prior to equilibrium. So what does that curve look like? It's going to be a downhill curve. So it's something like this. All right. And likewise, we also want a different state function that describes material equilibrium at constant temperature and pressure. So we'll do the same to define our Gibbs free energy, delta G. So for the Gibbs free energy, we will again start from my du smaller than equal to TdS plus dW, and with our basic calculus and also our definition of enthalpy. So we have H equals to U plus PV for your reference. So we can rewrite my dH minus dPV, which is U. So this one is your du writing out. smaller than or equal to TdS plus dW. Right. And then from there, we can rewrite it out. So dH minus PdV minus VdP, that's just calculus, smaller than or equal to TdS minus PdV, right? So your dW equals to negative PdV. Now, the negative PdV will cancel out on both ends, or you plus negative PdV on both ends, that's the same. And you get dH minus VdP smaller than or equal to dTs minus SDT. Again, this one is just calculus. Your TdS equals to, your TdS equals to dTs minus SDT. And we can simplify the terms a little bit by moving my Ts to the left-hand side of dH minus dTs smaller than or equal to negative SDT plus VdP. So the whole point of all these movements is we want the right-hand side to diminish when we're at constant temperature and pressure, because we want some kind of state function that equals to 0, or the differential of that state function equals to 0 at material equilibrium at constant Tp. All right, so that's why we're doing all these movements. And now it becomes more obvious. So on the left-hand side, we have dH minus Ts smaller than or equal to negative SDT plus VdP. Now, at constant temperature and pressure, dt equals to 0, dP equals to 0. So we get dH minus Ts smaller than or equal to 0 prior to equilibrium, material equilibrium, or dH minus Ts equals to 0 at material equilibrium for constant Tp processes. So from here, we define our Gibbs free energy, which is G equals to H minus Ts. Yes?
What does the 3 lines mean?
What's that?
What does like the 3 lines mean? Is that
3 line just means defined. So it's always going to be true, whatever condition it is. Delta G is just defined to be H minus Ts. Now, this one, when we say like D, the differential of H minus Ts smaller than or equal to 0, then this is a process-specific thing. So we can add this definition to our board here, which is G is by definition equals to H minus Ts. Or if we're doing the same kind of analysis here, thinking about how does my Gibbs free energy change with respect to time or the process of my equilibrium, well, we have G with respect to time, right? So what do we know? For constant temperature and pressure, we know that dG equals to 0 at material equilibrium, and we know that dG smaller than 0 prior to equilibrium, right? So the kind of curve we're getting is similar to what we see before. And you can label the position of equilibrium to be, okay, about here, my dG equals to 0, thus we are at material equilibrium. Right, so these parts are just definition of these terms. And again, if we're giving it a like finer definition with all the terms stated out, it's saying in a closed system capable of only doing PV work, the constant temperature and volume material equilibrium condition is the minimization of the Helmholtz free energy, where the Helmholtz free energy A is defined as internal energy minus Ts as an extensive state function. Likewise, the constant temperature and pressure material equilibrium condition is a minimization of the Gibbs free energy, where Gibbs free energy G is defined as H minus Ts. All right. Any questions before we move on? And well, some of the obvious example question you could be asked to solve is, well, what is delta G and delta A for a reversible freezing of, let's say, 1 mole of H2O taking place at 0 degree and 1 atm, only doing PV work. And we're giving you several information, including like Q fusion, CP of water, CP of ice, and also the density of water. You may not need all of them, but these are provided. All right, so a few of the things we know. First of all, it's asking us for delta H and delta A. One of them is just 0. Which one is it? Yes?
Delta G.
Yeah, so we're at constant temperature and pressure, right? So reading these kind of questions, if we specify that this is at 0 degree, 1 atm, it's the same thing as we specify constant temperature and pressure. So my delta G is just 0, right? What about my delta A? Now my delta A, we see that the delta A definition is A equals to U minus TS. Or the other way to put it is dA equals to du minus TdS minus SdT. Now, my temperature is not changing, so this term is 0 for constant temperature process. And taking the integration on both ends, we got integration of dA over integration of du minus integration of TdS. Or we have delta A equals to delta U, well, constant temperature, you can take temperature out, T delta S for this constant temperature and pressure process. All right. And well, what else do we know? We also have our first law of thermodynamics in this closed system. So we have delta U equals to Q plus W. And in this case, my negative T delta S term, you can do the derivation, but that's just negative Q. Or taking together, my delta A for this process is just the work reversible, which is negative PdV. Constant pressure, I take it out, just negative P delta V. Or actually, let me not skip any steps, just in case. Negative PdV, constant pressure. You take the pressure out, you get negative P delta V. And now with the density of the water, you can calculate what delta V is, and thus calculating what is our delta A. All right. Now, before we move on, let's go back to our system when we're talking about something that's there's a reaction taking place inside the system and the surrounding is at full equilibrium. And now let's link that with our definition of the Gibbs free energy and Helmholtz energy. Now remember, what do we have? We have delta S of my surrounding equals to Q surrounding over temperature, because everything is reversible in my surrounding. And we know that Q surrounding equals to negative Q system. So let's rewrite that to be negative Q system over temperature. And here we're saying Q surrounding plus Q system equals to 0. And let's set this to be constant Tp, so we can link it to our Gibbs free energy. Now in here, we see that at constant temperature and pressure, well, especially pressure, we have delta H equals to Qp. All right, so constant pressure, delta H equals to Qp. So my delta H of the system equals to heat of transfer of the system. Or the other way to put it, if I put this one back into here, we can say my delta S surrounding equals to negative delta H of the system over temperature. So far, so good. And now let's thinking about the system and surrounding together. Now, if we're thinking about my delta S of the universe equals to delta S of the surrounding plus delta S of the system. That's just using the nature of entropy as an extensive state function, right? Universe equals system plus surrounding. And, well, we already know my delta S of the surrounding equals to negative delta H of the system over temperature plus delta S of the system. So far, so good. What else do we know? We have also defined our Gibbs free energy. So using my definition of Gibbs free energy equals to H minus Ts at constant temperature. What do we have? Constant temperature, well, we can always write dG equals to dH minus TdS minus SdT. Constant temperature, this term goes to 0. You take integration on both ends. You get delta G equals to delta H minus T delta S. Or the other way to put it is we can write my delta G of the system. Or let me do this one. So in this case, we have my delta G equals to delta H minus T delta S. And we can put that back into our delta S of the system there. So we're getting my delta S of the system. So this one is just using here. We're just solving for delta S from this equation here, right? Delta G minus delta H, delta H minus delta G over temperature. That's where this comes from. So far, so good? Or this one, let me just rewrite. So delta S equals to delta H over T minus delta G over T for any constant temperature process. So what does that mean? So if we look at here, we have two different expressions of my delta S system. Or if I plug this one back in, plug this entire thing into here, what are we getting? We're getting my delta S universe equals to my, well, the negative delta H system and the delta H system over temperature will cancel out. So the delta S universe equals to negative delta G of my system over temperature. For this closed system, constant TP, PV work only. Or the other way to put it is the decrease in the Gibbs free energy of the system as the system proceeds to equilibrium at constant TP corresponds to the proportional increase in entropy. All right, so delta G and delta A are just developed so that we can describe entropy in a more straightforward way to find material equilibrium. Okay. I have 5 more minutes left, so I'm just going to do the physical meaning behind the Helmholtz free energy, and you can try the same logic apply to Gibbs free energy yourself, and next Monday, I'll do that with you. So let's look at it. So far we went over all these definitions, right? So again, what exactly does it mean? We call the Helmholtz energy a work function, and then we call our Gibbs free energy a free energy. What does that mean? Where does the work function and free energy comes from? So if we think about it, now we have this U minus Ts smaller than or equal to 0 at constant TB closed system thermomechanical equilibrium PV work only. Right, so what if, now let's drop this PV work only, thinking about other kind of work can also take place. That includes maybe electric work, you can have magnetic work, so anything that's not like expansion or contraction, non-PV work. So what do we have? Now we'll do the same thing. Thinking about it, we have, well, du smaller than or equal to TdS plus TdW. So doing the same thing, and then using TdS equals to dTs minus SDT, we have du smaller than or equal to dTs minus SDT plus dW. Now I cannot write my dW as negative PdV because we dropped the limit of PV work only. And what that becomes is du minus Ts smaller than or equal to negative SDT plus dW, or constant temperature. We have dA smaller than or equals to dW. Right, so for any kind of finite process, you can integrate on both sides. So we get delta A smaller than or equals to W. Now what is this W? This is the work done by the surrounding on the system. Or if we want to know how much work my system is doing on the surrounding, we can have my work by equals to negative of the work done on the system. Right, so imagine you're doing work on the system, so you'll have a positive W, then your system, then the work done by your system will be negative of that work done on your system. All right, so in this case, if we plug in this work by into this equation, I guess, or you times -1 on both ends, you get delta A smaller than or equal to negative work by. You time -1 on both ends and flip that inequality. You get delta A, negative delta A larger than or equals to work by. All right. So what exactly is it? And then what we end up getting is this expression. So for a constant temperature closed system, what does it have? It's the work done by the system for this isothermal process in the closed system. It's always going to be less than or equal to the change in work function A. All right, that's the amount of the work your system can do on the surrounding for these material equilibrium process, like reactions, phase changes, whatever. Right, so that's the amount of work your system can do on the surrounding. And that is why the Helmholtz energy is called a work function. All right, so that's the physical meaning of your Helmholtz energy. That tells you what's the maximum amount of work your system can do on the surrounding. So that's why chemical engineers cares a lot of the Helmholtz work function. So 2 more minutes, let me see if I can finish it. Gibbs free energy, the same idea, right? We apply the same kind of idea. We have H, like Gibbs free energy equals to H minus Ts. So you have G equals to U plus PV. So that's your enthalpy H minus, that's your enthalpy H. H equals to U plus PV minus Ts. And in here, we know that U minus Ts equals to A. So we can rewrite my G equals to dA plus dPV. All right. And same thing, we can write it out to be dG equals to dA plus PdV plus VdP. And then what do we have? In our previous derivation, we went over dA to be smaller than or equal to negative SDT plus dW. And we write it out as dg smaller than or equal to negative sdt plus dw plus pdv plus vdp. Now, considering constant temperature and pressure, now this one goes out, this one goes out. What we get is dg smaller than or equals to dw plus pdv. Or what does it mean? So if we think about the total work that's done on the system, so that's what this W means, dW means. That's the total amount of work done on the system, whatever form of work it is. But for that work, you can separate it into total work equals to work non-PV plus work PV. Now this work PV will equals to negative PdV. Right? Or the other way to put it is we can rewrite this one to be dg smaller than or equals to dw non-PV. Or doing the same kind of operation, talking about the maximum amount of your work your system can do on the surrounding, we can end up to be this expression. So the total work done by the total non-PV work by your system is given by the delta G number. Or the other way to put it, the quantity of negative delta G equals to the maximum amount of non-PV work output that's done by the system in this isothermal isobaric process. So again, it's called the free energy, right? Because as chemists, we don't typically care about how much expansion my reaction mixture is taking place. So that is why when we're talking about delta G, we're talking about that's the amount of the maximum non-PV work my system can do on the surrounding. And that's why it's called a free energy. All right. So far we defined lots of things. So next lecture will be a connecting all the dots. So next lecture will be thermodynamic relations and see, okay, now we have all these definitions. How do we connect everything together? So I'll see you on next Monday. That's my favorite lecture. We'll see.